Okay, our next presenter will be Kayla Schang from Macalester.
Okay, thank you very much. Hi, I'm Kayla Schang. I'm from Macalester, and I am the Macalester RASC-AL team lead this year. So today I will be talking about our contribution to this competition, which is the Human Exploration ISRU-based Mission Architecture, or HAIMA, Mission to Ceres design. We've been working with Dr. Tanister Veldhuis at Macalester as our faculty advisor, and Kevin Kempton from NASA Langley Game Changing Development Office as our technical advisor. So first, I will talk a little bit about the background for the project, and then I will get into an overview of the design we have been working on. So normally our rocketry team competes in rocketry building competitions where we can do a hands-on build and build some sort of rocket for various different competitions. Unfortunately, we were not able to complete an in-person build this year due to everything else going on, but we still wanted to participate in some sort of competition that would have a similar flavor to those rocketry competitions. So in summer 2019, taking a step back, I had worked with Kevin Kempton at a NASA internship supported by the Minnesota Space Grant in the Langley Game Changing Development Office, where we were expanding the Mars IceHome concept into the HAIMA concept. And I'll get into a little more detail of the HAIMA concept, but what is important there is that concept worked really well with one of the themes for the RASC-AL competition this year. So Kevin came to me and said, hey, do you want to get a team together to work on this competition and continue to expand that same concept? And so I connected the two, and we got the rocketry team together to form the RASC-AL competition team for this year. So a little background on the RASC-AL competition. It is run by the National Institute of Aerospace on behalf of NASA. They describe it as a competition that is based on full mission architecture, engineering design. What that means is that you are designing like a complete mission concept on whatever topic that might be. And it is really focused on the engineering design rather than any sort of immediate prototyping or something like that. So each year the competition provides around 3 to 5 teams, and each team 3 to 5 themes. Each team competing chooses one theme to participate under. And I will talk about the theme that we are on this year as well. For the competition itself, the team writes a proposal makes a concept video in the first round, and you'll see some clips from our concept video later on in the presentation. Then if you are chosen to continue on, you write a technical paper and then make a presentation and a poster for the RASC-AL forum, which usually happens in June. And just to clarify, for this year, everything is virtual. Typically, teams could meet in person to work on these sorts of things and design and brainstorm, but our team has been meeting entirely over Zoom. So to talk a little bit about the specific theme we're on, so we are doing theme 4, which is the human mission to Ceres. So Ceres is the largest object in the main asteroid belt, sometimes classified as an asteroid, sometimes as a dwarf planet, depending on what perspective you're looking from. And so our goal was to send the humans to Ceres. We needed to support a crew of 4 on a mission to Ceres and enable 2 crew members to land on the surface. Obviously, that is not happening anytime soon, as we still haven't made it to Mars. So this mission was to be scheduled sometime between 2035 to 2049, where the crewed component, where the humans are actually in space, happens in around 5 years or less. Another thing we need to do on the mission to Ceres is to be able to deliver scientific payloads to Ceres' surface. We also need to make sure that the humans are safe along the way. And so we need to make sure that our design mitigates all health risks. The major ones here are radiation. There's a lot of radiation out there in space. Usually when you're on Earth, you have a lot of other protection available to you, such as the magnetic fields around Earth, the atmosphere, even just the large planetary body. The nice, mostly solid body protects us from a lot of the radiation. Not all of that is available when you're just traveling through space. Additionally, space is a microgravity environment, which means there's almost no gravity in most of the places that you'll be. And so living in a microgravity environment for an extended period of time causes a myriad of health issues that we want to try to avoid. There's also some mental health components as well. We want to make sure that the crew is not feeling isolated or any of those other sorts of things that can happen when you're stuck with only 4 people for a 3 to 5 year long mission. Additionally, we looked a little bit at the logistics of the mission. The main requirement here was to fit within a $3 billion max annual budget, but we also looked at other things such as risks to the mission completion and other components. So first, I'll give an overview now of the overall HAIMA concept, because it does go beyond just the specific human mission to Ceres. So the HAIMA concept is aimed at enabling human exploration of the solar system through the use of ISOU technologies. ISOU technologies, in situ resource utilization, basically just means that you're trying to use stuff from the place you're going to rather than the place you're coming from. And that can do a lot of different things. Usually it helps reduce launch mass and thus the launch costs, because you are not having to bring all the supplies with you, which is a very handy thing since those are both very expensive. For this specific architecture, the in situ resource utilization comes in the form of using water collected from asteroids and or near Earth objects in order to enable different components of our design, which I'll speak a little bit more about which components those are. Now, that wouldn't necessarily be completed just by our architecture. There are other projects out there that are talking about different ways to enable that those technologies. APIS is one example, but it is still an important factor in our architecture. So for our design specifically, we can reduce the launch mass and cost with that water being used. And it also allows us to have an inflatable design rather than a solid design that you would launch, which really helps since the launch vehicles, they are difficult to design of a size big enough that allows you to have a comfortable size spacecraft. The other main component of this architecture concept is that it is not just about single vehicles at a time. The idea is to have multiple spacecraft that you would build up over time and then create a busing system throughout the solar system. So you could have, we call them cyclers. They could go between specific destinations or sort of stay on the same loop and hope that destinations intersect, such as if you were trying to go in the main asteroid belt somewhere. And that allows you to either hop along the busing system to go to wherever you need to go, or other missions could stop by these different locations along the busing system. That allows for easier exploration of further out locations in space. So now I'll talk a little bit about the vehicle design, since that is the main component of what we've been working on. So this is the HAIMA Crew Transit Vehicle, or the HCTV. And I'll talk a little bit about the overview on this slide and then go into some of the key features of the vehicle and the mission on the next few slides. So to sort of orient ourselves here, up here, these are the habitation modules. This is where the crew would spend most of their time. And this is the inflatable component that I was talking about earlier. So on the left is the inflatable position. This is what it would be like once the crew is all in space, so that they have some space to be in and can comfortably live in the spacecraft. On the right is the collapsed version, which makes it easier to fit into a launch vehicle. Down here is where all of the stuff that makes the spacecraft go is. So we have our propellant tanks and then the power and propulsion unit. And actually, the current thought for this design is to allow for a water-based propulsion system. So there's a nuclear thermal propulsion technique that can be modified to be used with water as the fuel instead. So these also may be able to be modified in their design to be able to take advantage of the fact that they will not be completely filled with fuel until they are in space. So those are the main components of the design here. And now for some of the key features. So first are a couple things to make the design better for the crew. We have a greenhouse in order to provide better food quality, a relaxing pastime in the form of gardening, and an overall mood boost. The crew will be out in space for a very long time with not a lot around them, so having some plants there is very nice. And also, even on the ISS, they get fresh shipments of food, relatively fresh, every few months, which is, so going for the 3 to 5 years of the mission with no fresh food and only prepackaged food would be very stressful on the crew. So we'd like to improve that aspect of the design with including a greenhouse. We also need to mitigate the microgravity issue. So we do that by rotating to provide artificial gravity. And here I'll play this again, but you'll notice in that middle frame there, the vehicle is rotating along that long axis, and that allows the crew to have a have not a microgravity environment, it will be around the gravity of Mars or so. So not quite as much as Earth, but enough to help mitigate some of those health issues. And then another key component of this design is the layered together. Up here would be the water for the radiation shielding that we will layer with the boron nitride nanotubes. We don't need to worry too much about what those are, but the key idea is that together those would protect the crew from the radiation that they would otherwise experience. So some other key features of the mission itself. So the vehicle would collaborate with a modified Dynetics lander to enable multiple crewed and uncrewed landings on Ceres. The Dynetics lander is currently designed for landings on the moon, but we can modify it for this Ceres application instead. And of course, having multiple crewed and uncrewed landings is very helpful as well, because you can complete more science while you are at Ceres. And additionally, any investments into this specific human mission to Ceres invests in future exploration, because this would be the first component of that HAIMA busing system I was mentioning earlier. And so it is a good investment in the long term, in addition to being a good initial mission to complete. So in terms of the competition, we will find out on March 29th, so in 2 days, whether our team has been chosen as one of the teams to continue on into the forum. So we are hoping, crossing our fingers, that we will be able to keep working on our design and refining it so that we can talk about it. Thank you. I can take any questions now.
Okay, great. Thank you. So the interest of NASA in this project is obvious. They were the ones who posed the problem. So I'm going to flip this a little bit on its head and ask you, what did you and your teammates learn, perhaps unexpectedly, about working on a NASA project that benefited you?
Yeah, I think, so I've worked on several projects that are more this flavor rather than the typical research flavor. And I think that it is a really interesting mixture of different fields. You have to consider a lot of different components to a project. So even things that might seem like they're only an engineering question, really you need to consider like the biology of the human body, because there are real live crew members who are going to be living in that vehicle and things like that. So I personally find that to be very interesting. There are also just a lot of components about space exploration that perhaps people vaguely know about, but haven't really thought about in detail, and trying to figure out how to design for all of those different contributions in order to make a safe mission for the humans, I think is also a good experience as well.
Did the fact that you were remote when you were working on this project slow you down, or not really at all?
Well, I think there's always a little bit of logistics in terms of you're not seeing people in person to remind people to complete different components of the project. But I think overall, we've been working pretty well virtually. We all sort of knew that was going to be the case going into it. And so we've been pretty good about communication and getting things done that way.
Questions from anybody else in the room?
So you're going to have a greenhouse in this proposal. Can you talk a little bit about what the requirements for that are? Like, are you planning on using human waste as a fertilizer, or is that, what's your thoughts about that? And how much water does it take to run a greenhouse on a ship like this?
Yeah, so another extension of the Mars Ice Home project. So I suppose I didn't clarify this. The Mars Ice Home was basically our spacecraft, but on Mars rather than traveling through space. And so another team working with Kevin Kempton in that same summer worked on creating a greenhouse that would fit within the Mars Ice Home design. So also sheltered by the ice around it and all of those different components. So our design, so far, we've basically just said, hey, someone else has already designed this greenhouse that would work well with a very similar setup to ours. And so we're going to branch our design off of that. So we haven't worked too much about the specifics of that system quite yet. We'll perhaps do some more development for the forum. But in terms of the different concerns, I don't think that we would be too concerned about having enough water, since we will be completely surrounded by ice. And we'll be able to collect additional ice on the outside of that layer. So you don't want to use up all your radiation shielding, obviously, but it is a good storage method. It's pretty easy to expand it enough to include all the water that you might need for the humans to consume and for the greenhouse to use. Unfortunately, I don't have numbers right off the top of my head about how much water that would be, but I think that there shouldn't be too much of a concern with that in the long-term design.
Have you watched the latest George Clooney movie, which talks about or includes a spacecraft that has ice on the outside and how they need to tap into that in the middle of their mission?
I have not, but it sounds like a team bonding activity we should pursue.
You should pursue it, and don't do it that way.
Okay.
Okay, thank you. We will go on.